Good day. I am Shervin Azadi, co-founder and researcher in Genesis Lab at TU Delft, Faculty of Architecture and Built Environment. Today I will present the GoDesign project researched and developed by my colleague Dr. Pirouz Nourian and me, which funded by ACTI Agenda on Verpan Overhigh 2017 until 2020. Today's presentation is particularly about the novel outcome of this project, a modular generative design framework for mass customization and optimization in architectural design. First, I start by establishing various complexities that are involved in a design problem. In the design process, we deal with multiple small problems that each of which can be complex on objective, subjective, and intersubjective fronts. We establish a spectrum from physical complexity to human complexity and elaborate on each type. The most concrete and tangible complexity in the design process is multidimensional or spatial complexity, which refers to the difficulty that arises from entanglement of spaces and physical elements in 3D space. Next is multi-criteria or directional complexity, which refers to the difficulty of satisfying and abiding by various criteria simultaneously in the design process. Next, multi-actor or consensual complexity refers to stakeholders' conflict of interest that arises from their differences in their priorities. Finally, multi-value or normative complexity, which engulfs the difficulties that arise from uncertainties and ambiguities in human perception and communication. By adopting the decision-making perspective, we slice the design process into discrete decisions that each one of them can be formulated mathematically to appropriately address the relevant complexities involved. Furthermore, we propose to prioritize abstract decisions over more concrete ones to reduce the interdependency of decisions in the design process and consequently decrease the complicatedness of it. We propose a three-phase hierarchy: planning, configuring, shaping. I will elaborate on each one of these phases in a moment. The important point here is that each phase has different set of complexities and may require different methodologies to address them. We envision a spectrum of methodologies that can be adopted, from the most objective decision-making approaches that is mainly based on mathematical derivation and optimization, to hybrid methods such as decision support systems and gamification that allow the actors to co-create a decision while providing objective assessment of alternatives, until the most subjective methods such as grammatical itemization through generative grammars. The first phase, planning, focuses on the relational decisions. What are the spaces and their requirements? How close the spaces need to be to each other? How important is each one of the criteria for each space compared to other spaces and also compared to other criteria? The main constraint of this phase is consensus. Actors need to agree on one set of relations. The consensus can be reached through conventional negotiations or through decision support mechanisms and serious gaming. The output of this phase is a hypergraph that describes all the relations that has been specified. Second phase is configuring, that focuses on satisfying the requirements and relations by allocating them in a discretized volume. The problem in this phase is the most spatial. How should we configure the space? The main constraints in this phase is local and global spatial validity constraint that has been set in the planning phase. The output of this phase is the decision matrix denoted with X. The structure of this matrix is comprised of a set of density vectors corresponding to each space. Each of these density vectors has a very similar structure to density vector in topology optimization. The last phase is shaping. The decisions in this phase are the most concrete decisions. What are the exact geometric and materialistic attributes of the physical elements of the building? The main constraints in this phase is to separate different spaces with an appropriate physical element. For example, if the separation is spatial but not visual, then a window is placed. If the separation is visual as well, then a wall is required. If the temperature is controlled on one space and it is not on the other, then thermal insulation is needed as well, and so on and so forth. The output of this phase, by mathematical definition, is a surface mesh. However, this mesh can be spelled out as a beam model as well. This framework focuses on offering a mathematical formulation that supports a variety of methodologies to find a solution for the design problem. Thus, in the primary phase, we have applied this framework in educational and research context. In the educational context, the framework paired with extensive Python programming workshops has been used in MSc and BSc design studios at TU Delft, the result of which you can see on the right. In the research context, the framework is currently the basis of an online urban redevelopment game that brings different stakeholders of the project together in a gamified setup and lets them develop intervention alternatives with respect to diverse spatial quality criteria ranging from environmental factors to heritage related attributes and values. Regarding the implementation, currently all the required computational tools for this framework are implemented in the Topogenesis Python library. This has been the basis for the application of the framework in the aforementioned educational and research setups. On the generality, as it has been mentioned earlier, this framework supports a spectrum of methodologies from mathematical derivation and optimization until decision support systems and serious gaming. Furthermore, the mathematical formulation can incorporate any quality criteria that can be formulated as a function of space. The main limitation of this framework is that it is not easy to embed particular geometric concepts in the initial phases, and that is explicitly because of the decision to prioritize abstract decisions over geometric ones. Regarding the future works, it is important to note that this framework is a mathematical foundation within which different spatial quality criteria need to be formalized and benchmarked to operationalize this framework. Furthermore, this framework opens up the possibility to apply a platitude of decision-making methods from operations research and MCDA, optimization methods, and machine learning algorithms. More specifically, methods from reinforcement learning because of the similarity in the problem formulation.